Well, hello, good people. Today we are going to be talking about color mixing. This is the second part of a little video series. It's all about color mixing. Now, last time when we saw each other, we tried this little experiment here where we had a little image, and I asked you to stare at this image for a good amount of time. And then after you stared at this image for a good amount of time, I asked you to, or I changed the screen, and then you saw what we call an after image on the following screen. This is an example of retinal fatigue. Now, we showed that this happens, and then we talked about rods and cones and all of those kinds of things, but we didn't really talk about why this happens. Well, in order to understand why this happens, you have to understand a little bit about how, please excuse the bells, you have to understand a little bit about how light works. So today we are going to talk about how light works, how you can mix different colors to get other colors, and this topic is all about color mixing. Now, when it comes to color mixing, there are actually two ways to mix color. One type of color mixing is what we call color addition. Oh no, color addition. Color addition happens when you mix light together. Like if I mix two different frequencies of light, like a purple light and a blue light. And then the next type is called color subtraction. We'll talk about why it's called color subtraction here momentarily. Color subtraction happens when you mix different pigments together. That happens when you mix things like dye or paint or ink. That's mixing pigment. So we'll start today by talking about color addition, what happens when you mix different colors of light together. And then we'll talk about color subtraction, what happens when you mix paint or pigment or ink together. We'll start with color addition. It turns out that when your elementary school art teacher taught you, that there are three primary colors. And those three primary colors your elementary school teacher said are red, yellow, and blue. Well, as it turns out, those actually aren't totally the three primary colors, and I'm sure you're feeling very disillusioned right now because you thought your whole life that those were the three primary colors, and those are the three primary colors in art class. They're not the three primary colors in physics. Now, we'll see later why your art teacher told you that the three primary colors were red and yellow and blue, but in physics that is not the case. In physics, the three primary colors for color addition, mixing light, are red and green and blue. In color addition, we say that the three primary colors are red and green and blue. Well, why? Because you have red cones, green cones, and blue cones. So all of the light that you see in the world is a combination of what your red cones are seeing, what your green cones are seeing, and what your blue cones are seeing. So we call these the primary colors because that's the way that your brain is going to interpret the world, is through combinations of these three colors, of these three frequencies of light. That's why we say that red, green, and blue are the primary colors for light addition. We'll talk about why your art teacher used to tell you that primary colors were red and yellow and blue when we get to light subtraction, which is what happens when we mix things like paint. To start, this is hard to show you because I do a whole demo in class to see it, but I'll show you a little picture here of, oh wow, that was crazy. I'll show you a little picture here of what happens when we mix different colors of light. Here's a picture of three different lights being shown onto a wall. There's one light that's being shown onto this wall that's a green color here. Another light on this wall that's a red color here. Then a blue light being shown onto the wall here. And you can see that in the places where those light colors mix, we get new colors. These are our three primary colors here. This is blue here, this is red here, and green here. Then in the places where they mix, we see that new colors develop. Here, between blue and green, we get this color right here, which we call this color cyan. Oh no. Oh wow, that is an embarrassing C. Let me try again. We call this color right here cyan. C-Y-A-N. This color right here, where the red and the green mix, check it out. Weird, but the red and green mixing gives you yellow. When a red light and green light mix, we get yellow. And then finally, in the place where red light and blue light mix, we get a color that we call magenta. Then you can see at the place where all of them mix, where red light and green light and blue light all mix together, we get white here in the center. In color addition, the more colors of light that you add together, the closer and closer and closer that you get to white. White is a combination of all of the frequencies of light. This leads us to initially 4 color equations that we'll start with. Here are your color equations. Okay, here are your color equations. We say that, like you saw in the picture, if we add together red light plus, oh, this is going to be obnoxious because I'm going to have to change my pen a lot, but it's so worth it. Okay, we say that if you add together red light and green light, and this one is going to be weird. This is the weirdest one for students, but you could see it in the picture. It's very true. If you add together red light and green light together, you get yellow light. Then we also saw from the picture that in the places where green light and blue light mix, places where green light and blue light mix, we get cyan colored light. Wow, it's literally called cyan. Oh, it's so great. It's so happy. Okay, we get cyan colored light. Green and blue together make cyan. And then lastly, in the places where you have blue light mixing with red light, blue light mixing with red light, we get magenta. Now, I'm not really seeing a magenta that I really love here. Magenta is kind of a weird mix. It's like a purplyish, pinkish kind of color. I'm going to go with this purple here, and you're going to have to just believe that it's magenta and know in your head and your heart that it's magenta. So this gives us 3 equations and 3 colors. We get yellow, cyan, and magenta. And the last thing that's true is if we add together red light and green light and blue light, all in combination with each other, add all 3 of those together and you get white light. Red light plus green light plus blue light is equal to white light altogether. These are your 4 initial equations for color addition. And you do need to have them memorized in terms of you need to know what colors add together to produce what other colors. You saw that we have a very nice color wheel here. I'll go back over here. A very nice color wheel that we can form that looks kind of something like this. I'm going to take this image that's actual light and then using presentation magic, watch Google Slides, kabam, turn it into another picture. Okay, here's what we have. This is red light. We got green light. We got blue light. Here between green and blue, we got cyan. Here between red and green, we got yellow. Here between red and blue, we got magenta. Here in the center, we have white. This gives us 3 primary colors of light and 3 secondary colors of light. The 3 primary colors are red and green and blue, and the 3 secondary colors that are made up of the primary colors are yellow, cyan, and magenta. Here's something that's interesting is we also get what we call complementary colors. Check this out. If I add together red light and cyan light, red light plus cyan light equals white light. And this should make some sense to you because cyan is made up of green and blue. And if you have red plus green and blue, well then all together you get white. Blue plus yellow also equals white. And once again, this should make some sense to you because you have blue over here. Yellow is made up of red and green. So you got blue plus red and green all together. That makes white. If you want to turn magenta light into white light, magenta is made up of red and blue. You add red and blue and green and you get white. So magenta and green are what we call complementary colors. Complementary colors live across from each other on our color wheel here, and here, and here. And these complementary colors for color addition add to create white light when you combine them all. Let's write down what our complementary colors are over here. Here are our complementary colors. Oh, first I wanted to write this. These three right here are our secondary colors. Our secondary colors. These three here, these are our primary colors. And then lastly, we have what we call complementary colors. For our complementary colors, we have red, and red needs green and blue. Red and cyan together are complementary colors. And then I think I went with the other cyan. Let's keep it consistent. Okay, red and cyan together are complementary colors. Green plus red plus blue equals white, so green and red plus blue is equal to magenta. So green and magenta, again, I don't have a great magenta here, but green and magenta are complementary colors. And then finally, blue plus red plus green equals white, so blue plus red and green, well, that's blue plus yellow altogether equals white. And these are the three sets of primary colors, red and cyan, green and magenta, and blue and yellow. These are what we call the complementary colors. And they live across from each other on the color wheel. Those are pretty much all of the equations that you need to know in order to understand this retinal fatigue activity. Here's the idea of the retinal fatigue activity, where you stare at the flag and then you see the opposite colors. When you look at this flag, let's scroll up here. Whoa, okay, but let's not freak out about it. We can do it like all relaxed and stuff. Okay, when you look at this flag right here, what you see is you're looking at a color, we'll start with the top corner. You're looking at a color like yellow. Yellow is made up of red light and green light. When you stare at this image, you are getting messages sent to your cones in the back of your eye. And the messages that are sent from this little square right here are sent to very specific cones in the back of your eye. And they say yellow, 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 which activates your red cone and your green cone. So your red cone is saying, I see red, I see red, I see red, I see red. And your green cone is saying, I see green, I see green, I see green, I see green. And so then your brain says, oh yes, my red cone is firing and my green cone is firing. That must mean that there's yellow there. But what happens is, if you stare at this image for a very, very long time, then your red cone is saying, I see red, 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 and then your green cone is saying, I see green, 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 and then they both get very tired. And your red cone and your green cone get very, very tired. When we flip to the next page, just like this, your red cone and your green cone are very tired from staring at the image, so they're already a little tuckered out. But your blue cone is still ready to go. It's nice and well rested. And so when we switch slides really quick, what happens is your eye can see, well, let me start here. The light that's coming from the white screen is made up of red light and blue light and green light. But your red cone and your green cone are both very tired. So the only color that's left that you can see as strong is blue. And so you see blue where you used to see yellow because your red and green cones are already tired. Hey, take a second. Can you explain how you would see red if you were staring at this cyan color? Notice that with a retinal fatigue activity, anytime you have a retinal fatigue activity, you are always going to see the complement of the color. So if you stared, you got it, buddy, you can do it. Yes, perfect. Way to go, computer, so proud. If you stared at red for a very long time, your red cone would get tired, your green cone and your blue cone would be very active, and you would see cyan as your after image. If you stared at blue for a very long time, your blue cone would get very tired. Your red cone, then when you switch your point of vision, when you are looking at a new place, your red cone and your green cone would be ready to go. So you would see yellow, but you wouldn't see blue anymore. So you will always end up seeing the complement of a color when you do a retinal fatigue activity. That is a little bit about color mixing. We now have 3 applications about color mixing that I want to talk with you about. And then after we talk about that, that is all for color addition, and then we'll talk about color subtraction next. Here are the 3 examples that I wanted to talk to you about today. The first example is, what if we took an American flag? Please excuse the bells. What if we took the American flag and we walked with the American flag and we took it all the way down the hallway into the darkroom at Devlin? Now, if you've ever been in the Devlin darkroom before, then you know that the Devlin darkroom is lit by entirely red lights. This is to protect your photo paper from getting exposed. If your darkroom is lit by entirely red lights, then your photo paper, when it's underneath the red light, it won't turn immediately black. But if it's exposed to any other frequency of light, that'll turn your photo paper black, and that is very unfortunate because then you can't have a nice image. So anyway, that's like a whole chemistry lesson. Let me know if you're interested. But for today, all that you need to know is that the darkroom is lit by entirely red lights. Hey, if you went into the Devlin darkroom and you brought the American flag with you, what color would the American flag look like under the red lights? Well, here's what you would see. You would see that the American flag has really 3 parts to it that I am not going to draw in full detail, but we'll just get a general gist. The American flag really has 3 parts to it. It has the blue box that has all the little stars right up here in the corner. There's your nice little blue box with nice little white stars. Then it has red stripes and white stripes. And again, you have you have way more stripes than I'm going to draw, so this we all know is a lie. Okay, so here's what you would see. When you go into the Devlin darkroom, the red stripes under the red light would still appear red. Because the reason why they look red in the first place is because those red stripes reflect red light. If they're in the Devlin darkroom, the red light is coming down, that red light would hit the red stripes, and the red stripes would reflect that red light back to your eyes. So you would see the red stripes as red. But what about the white stripes? Well, if you went into the Devlin darkroom, in normal light, the white stripes would reflect red and green and blue. But in the Devlin darkroom, there is no green and there is no blue for the red stripes to reflect. So the red stripes reflect the only color that they have available to them, which is red. So the white stripes would look red. You would have red stripes next to red stripes, which would be a very uninteresting stripy pattern. The blue rectangle up at the top here, this blue rectangle, the blue rectangle is blue because it reflects blue and absorbs the other colors like red and green. If you put the blue rectangle under red light, well, blue things that are blue because they reflect blue, but they absorb red and green. So what would happen is that red light would come down, the red light would get absorbed, and there would be no blue light for that blue square to reflect. So the blue square would look black. It would look like it's reflecting no light because it is reflecting no light. The red light comes in, it gets absorbed, and there is no blue to reflect. So what you would have is you would have a totally red flag that has no nice distinguishing contrast between these stripes. You'd have a really red section and then another red section. And then here in the corner, you would have a black square, a black rectangle with little red stars because the white stars would reflect red light. And so it would appear red. There's your first application question. Your second application question, I'll leave up to you. Actually, no, then we'll talk about it. I was going to say it's all up to you, but it's not all up to you. Say that it was the day of the great performance and all of the cast members came to the stage and they all were wearing navy blue dresses for the graveyard scene when they were all supposed to be wearing black dresses. Is the show ruined or is there any way to save it? Well, if you're part of the lighting crew, you say, for sure there's a way to save it. If you want this blue dress to look black, you got a few options. you could shine on this blue dress. You could shine in red light. The red light would get totally absorbed. You could shine green light on the blue dress. The green light would get totally absorbed. Or you could shine yellow light, since yellow light is a combination of red and green, and that would get totally absorbed. And so as long as all of the colors are getting absorbed, the blue dress would look black. Now, here's a little stipulation and a little tip for you if you ever do find yourself in this situation. My recommendation to you, although theoretically, if everything were perfectly perfect and everything was very nice and monochromatic, you could use red light, green light, or yellow light, and any of those would work fine. But my recommendation would be to use red light, and here's why, is that no color that you're going to see is going to be a perfectly pure version of that color, a perfectly monochromatic version of that color, with the exception of light that comes from a laser. If you have light coming from a laser, the light coming from the laser is one frequency. But if you have a blue dress, the light from that blue dress isn't just all one frequency of blue. It's likely some blue with some of the next door neighbor frequencies. So it's some blue with a little bit of purple frequencies and a little bit of green frequencies in it. So if you shine green light on the dress, odds are that dress is actually reflecting a little bit of green light as well. If you shine green light, then the dress will probably most likely look green because it has a little bit of green that it's reflecting. If you shine red light, though, you're probably that's probably your safest bet, because red light is very far away from blue light. And so in terms of like on the electromagnetic spectrum, on the visible light spectrum, it's a very different frequency. And so the odds of that dress reflecting much red is very, very low. So red light is probably the best bet for which color light you want to shine on the dress to save the show. One last application for you, and that will be all for color addition, and then we'll talk color subtraction. What happens if you take a yellow light filter and you hold up a yellow filter to the blue sky? What color would the sky look? Well, you have to remember that yellow filters look yellow because yellow filters transmit yellow light. They allow yellow light to pass through. But yellow filters also absorb other frequencies of light. So they let the yellow pass through, but they absorb colors like red or colors like purple. Here's what would happen. If you held the yellow filter up to the blue sky, blue light would come in. Yellow filters allow yellow light to make it through, but they absorb other frequencies. And so, ideally speaking, if you held up a yellow filter to a perfectly blue sky, that perfectly blue sky would look black. But this is where students get confused, because students say, you know what, Miss Wilson, that all sounds very great and fun and all, except that I have worn yellow filters before. They say my ski goggles have a little bit of a yellow tint to them, or I've worn sunglasses that have a yellow tint. And they say when I have my yellow sunglasses on or my yellow ski goggles on, the sky doesn't look black. It is not as though I look up into the sky and I see a massive looming darkness overhead. They say, no, it does not look like that. So they said, Miss Wilson, you must be lying to me. Well, here's the truth of the matter, is that no yellow filter is a perfect yellow filter. And also, the sky isn't a perfect blue. So the yellow filter is mostly supposed to let through only yellow light. But in reality, that's not what it does. It lets through yellow light, but it also lets through some of the nearby frequencies. So it also lets through a little tiny bit of red or a little tiny bit of orange, and it also lets through a little tiny bit of green. The sky isn't a perfect color blue. It is blue, but it also has some nearby frequencies too. So the sky is blue, but it's blue with a little bit of purple mixed in, and it's also blue with a little bit of green mixed in. So here's what happens. You hold the yellow filter up to the sky. Green light, blue light, and violet light are all on their way to the yellow filter. The yellow filter only lets through red light and yellow light. Well, it only lets through yellow light, but it also lets through a little bit of red light and a little bit of green light, and everything else it absorbs. So the blue light and the purple light come in, and the yellow filter absorbs the blue light and it absorbs the purple light. But some of the green light actually makes it through to the other side. And so when you look on the other side of the yellow filter, you'll see that the sky on the other side of the yellow filter looks green because the little bit of green light from the sky gets to make it through that yellow filter, which is not a perfect yellow filter, but actually does in fact let through a little bit of green. And those are some examples of color mixing. What you see is that there are 3 primary colors of light, there are 3 secondary colors of light, and then you have 3 sets of complementary colors. All of the primary colors add up to white, and also the complementary colors likewise add up to white when you add them together. We looked at how retinal fatigue works, and you understand that concept of how your eyes will always see the complement when your cones get tired. We also saw 3 examples of color mixing or light mixing, how colors are not actually really pure. The light from the sky is not really a pure shade of blue, and yellow filters don't only filter through yellow, but they actually allow some other frequencies on the sides too. And we saw how different colored objects would look under different types of light. That's a little bit on color addition. In our next video, which will be a nice and short video, we'll talk a little bit about color subtraction, and that will conclude our mini series on color mixing. I hope you have a wonderful, wonderful rest of your day. Bye, good people. Wait, I always forget how to end it. Oh, this is just, it's so awkward and uncomfortable. Do you feel awkward and uncomfortable? Me too. Let's see. Oh, yes, there it is. Okay, now bye for reals, good people.